Hey guys, I'm Pat Kelly. Okay, we are supposed to use mathematical induction to prove the formula that they give us here, okay? So now mathematical induction is very cool, but it does take a little bit of work. So just like I've done, you might want to roll your sleeves up here. Got some stuff to do. Most importantly, you always want to lay out there are two main steps for mathematical induction, okay? So always show that type of work. And always, the first step is you want to show that this statement is true for your first value of n. In this case, they're saying n greater than or equal to 1. So we need to show that this formula is true when n equals 1. So that means looking at that expression they gave us, we just want to put a 1 in for n. So if I'm putting a 1 in for n, realize what that's saying on the left-hand side of the equal sign. You only have the one term, okay? The plus dot 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 says go on until you get to 2n, but my n is 1, so you're actually done right away. So 2. And we need to ask ourselves if that equals the right-hand side of the formula, but again, where n is 1. So the right-hand side is here. I'll put a 1 in. 1 times 1 plus 1. Pretty easy arithmetic, I think, right? 1 plus 1 is 2. Multiply by 1. We do get 2 equals 2, right? Check mark. That's done. All right. That's the first step in mathematical induction, is to show that the formula works for 1. The second step now then, my second step, in fact maybe I'll even switch here, because with your second step you do two things. The first thing you do is to assume, and what we're going to assume is the original statement but with a k in place of n. Okay, so let's write all of that out. Let's see if I have room here. 2 plus 4 plus 6 plus, let's just say dot dot dot. We know the pattern now. It does end at a 2k on the left-hand side, and equals the right-hand side but with a k in place of n. K times k plus 1. And I am not putting any kind of question mark over that equal sign, because it's not a question, it's an assumption. We are assuming that that's true, right? And then the next thing you do, still in step 2, but what we want now is to look at that same equation, that same formula, and we want it to be true for k plus 1 now. Okay, so take a look at that big long expression, and we want it to be true where I put a k plus 1 in place of the n. So 2 plus 4 plus dot dot dot. I'm intentionally going to skip some space here. Okay, I'm going to come back in a second, but the dot 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 should go all the way up to 2 parentheses, and in place of the n, I'm putting k plus 1. You might notice, you should notice, I put parentheses there because the multiplication by 2 needs to happen to the entire binomial there. And that is supposed to, or we're hoping, or we really want that to equal the right-hand side, but with a k plus 1. So k plus 1 in place of the n. That's that n. And the second part there is n plus 1. I'm going to put a k plus 1 in for n, so that's actually k plus 2, right? K plus 2. All right, let me grab another color here, because again, this equation is something that we want. We need to show that that equation's true, given this assumption statement, okay? And that's why I was going to cheat here a little bit, that space that I left, because this sum that I did with the dot dot dot, it goes all the way up to 2 k plus 1. Think for a second what would have been right before that last term. What would have been right before that last term would have been plus 2k, and then plus the 2k plus 1. Make sure that makes sense to you. It's an important step that we need to use in a minute here. So the term right before that guy would have been this guy. Okay, it's just 2 times something. Let me go back here. 2 times something, 2 times something, 2 times something. So 2 times k, and the next something would be 2 times k plus 1. Whew, okay? All right. The reason why that's so important is because now, you know what? I'll even switch another color out here. All of this up to the 2k is right here for you, or for me, for us, in this step. So I can replace it with what it equals from our assumption. Okay, I'll continue back in blue here, but what's underlined there is going to be replaced with k times k plus 1. And I even maybe use a double underline there to code this, so that's the same expression that's underlined over there, double underline. Let me pick back up with the work here, plus the 2, k plus 1, which is from right above in my work, right? And I still want that. I haven't shown it's true yet, but I really want it to equal, I'm going to leave the right-hand side alone, k plus 1 times k plus 2. And now what you do with these problems is you play around a little bit and try to get the one side to look like the other side. And as is almost always the case, the playing around that you do is algebra. So your algebra skills are up to snuff. I'm sure they are. What I would do here on the left-hand side is factor out a k plus 1. Okay? K plus 1. If I factor that out, you can see I have 2 terms separated by the plus sign, and here is one k plus 1, a k plus 1 in the first term, and also a k plus 1 in the second term. So I'm factoring that out. So what's left over? Well, from the first term, the pink underline's gone, and so all I have left is the k there. Plus drops down from there. This k plus 1's gone, and all that's left is a 2. And you remember our wish list? What we wanted? We wanted this to equal k plus 1 times k plus 2. Our wish has come true. A little poem there for you, I guess. This worked. That's awesome. That's what we wanted. That's mathematical induction. Okay. To wrap this up, by mathematical induction, we have proven this statement to be true. Okay, so this is a formula now that we've proven is true. You deserve a good pat on the back for that one. Okay? Reach around, give it to yourself, and then go try some on your own.